Okay, so that's literally the point. Anyways, so now, so populations can grow exponentially when conditions are favorable. So yeah, so look, so when we say exponential growth is always the assumption is that you have unlimited resources. But again, it's not really always about unlimited resources. Usually your population is too small, or like your individuals don't take that much resources. So the resource that you have is enough, is more than enough for them. So yeah, so normally, by the way, they usually collapse, like, I mean, like boom, like when they run out of resources. But anyways, so we have two different types of exponential growth. So, and they're growing like very fast. There's a geometric growth and there's exponential growth. Geometric growth is when your population actually only they don't reproduce, they don't like they have breeding season. So they only breed in certain year. I'm not saying once a year necessarily, but I'm saying like it's not all the time. So that's one, like the blue one, that the blue one is actually showing like the, see, like for example, the numbers jump. The red one is actually for the exponential growth. Again, there, you end up getting the same numbers though, but I mean, the chart would slightly look different in terms of whether you have a continuous number for the exponential growth, which is indicating like, for example, like bacteria, they're constantly replicating. Or like, again, a lot of animals like chicken, they actually grow all the time. They don't have a season. Or like we don't have either. Like we would have, again, I mean, I'm not saying we have, I mean, technically the humans population on Earth are growing exponentially though. Yeah. So these guys have breeding seasons. These guys don't. But again, the key to both of them growing like crazy is when the conditions are favorable, aka unlimited resources. So they're saying that, yeah, so if you wanted to exhibit these exponential growths that look like this on a straight line, you can actually use a logarithm of the log of their population increase per unit of time. Then it would look straight. Okay, so when you're talking about population growth, we have two variables that actually indicate like how a population is growing. There's lambda, which is we're going to talk about now, which is actually for the geometric growth. And then we have R, which is actually for the exponential growth. And they are different actually. So you see, so again, I believe these equations are actually given on the formula sheet in an exam. But again, when you look at the sample midterm, yeah, so yeah. So yeah, so so it's saying that nt plus 1, again, these are very basic formulas, by the way, so don't freak out. Like these are very basic. So this is like a population in the future. That's your growth in that period, and that's your population size now. So the growth times your population size now will show you like how big your population will be after that period. So this is per period. Yeah. And again, so you can actually just like play with this. So I mean, to be honest, so they're saying like this is a one-time thing. This is like for example, like after, again, remember like this geometric growth. Like for example, like imagine this is your yearly growth. And they say, yeah, so how big so if your population is 100 now, and your growth is like something. So yearly. Then we say like, okay, so after 2 years, how big the population is going to be. So then you would put 2 there. That's what it is. So this is actually something very important. So population growing, population declining, population constant. So for the lambda, so when lambda is greater than 1, it's growing. When lambda is greater than 1, less than 1, it's declining. And when lambda is equal to 1, that's constant. So now let's talk about R. So, and then that's the geometric one. Cool. Yeah, so like what might this the value of the lambda be when the population is decreasing? I mean, yeah. Again, so this is actually kind of like the mouse example. So they're saying that they're saying that, for example, like right now they have, oh, that's the same example actually. Never mind. So yeah, so they're saying like, is it the same at every step? Yes. If it's a geometric growth or exponential growth, it's supposed to be the same. Does it have to be the same? No, but it's not like it goes up and down, up and down, up and down. When it's logistic growth, which is a different type of growth, we still use lambda for that one. It declines. So it's until it plateaus. So it's not like it can fluctuates. So when it comes to exponential growth, so again, you see, look, dn over dt is actually mentioning, so how many new individuals will be added or removed per unit of time. That's not your new population. That's like how fast you're, by the way, this is not, I know it's not derivative. Like imagine like that's like a delta n over delta t. What's the change in a population size over time? Remember, like I'm not a like a I don't remember like anything about like calculus and stuff. So don't think, oh my God, so much math. Anyways, so yeah, so this is like for exponential growth. And so for the R, this is not based on 1. It's actually based on 0. If R is greater than 0, you have population growing. When R is less than 0, population declining. When R is equal to 0, the population is constant. Yeah. Yeah, and then they're kind of saying like these two numbers are related, but I don't think we need to know that. Okay, so you see again, so obviously the population is declining here. So lambda less than 1 and R is less than 0. Yes. Population is constant, so lambda is equal to 1 and R is equal to 0. And then the population is increasing like crazy. So lambda is greater than 1 and R is greater than 0.